Hello friends, welcome back. In the last worked example, we computed the gradients, the operator that takes a scalar field and gives back a vector. Today we meet a different beast, the divergence. The divergence takes a vector field and returns a scalar. So if A is a vector at every point of space, nabla.A is a number at every point. Geometrically, the divergence at a point measures the net outflow of the field from that point per unit volume. Think of A as the velocity of a fluid. If divergence is positive, more fluid leaves a tiny box around the point than enters. There is a source inside. If divergence is negative, more fluid enters than leaves. There is a sink. If divergence is zero, whatever flows in also flows out. The field is incompressible, or as we say in electromagnetics, solenoidal. This is more than fluid dynamics. In electrostatics, the divergence of the electric field at a point equals the charge density there divided by epsilon zero. That is one of Maxwell's equations. So divergence is a way to ask where are the sources of the field. The divergence formula has the same shape in every coordinate system, but with different factors that account for how the volume element changes. In Cartesian, nabla.A equals partial AX over partial X plus partial AY over partial Y plus partial AZ over partial Z. Three partial derivatives, no extra factors, perfectly symmetric. In cylindrical, nabla.A equals 1 over rho times partial of rho times A rho with respect to rho, plus 1 over rho times partial of A phi with respect to phi, plus partial of AZ with respect to Z. Notice the rho appears inside the rho derivative. That is the volume element distortion. In spherical, the radial term is 1 over r squared times partial of r squared times ar with respect to r. The theta term is 1 over r sine theta times partial of sine theta times a theta with respect to theta. The phi term is 1 over r sine theta times partial of a phi with respect to phi. The deeper y. In non-Cartesian systems, the volume of a tiny box depends on where it is. Near the cylindrical axis, a small phi sweep covers little arc. Far away, it covers a lot. The divergence asks for net flux per volume, so the formula must include those geometric factors. We will see them in action right now. Worked example 1. Cartesian. Take A equal to x squared y x hat plus y squared z y hat plus z squared x z hat. Our point is P equals 1, 2, 3. We want the divergence at P. 3 steps, one for each component. Step 1. Take partial of ax with respect to x, where ax equals x squared y. The y is a constant when we differentiate with respect to x, so we get 2xy. At p, that is 2 times 1 times 2, which equals 4. Step 2. Take partial of ay with respect to y, where ay equals y squared z. Now z is the constant. The derivative is 2yz. At p, that is 2 times 2 times 3, which equals 12. Step 3. Take partial of az with respect to z, where az equals z squared x. With x constant, the derivative is 2zx. At p, that is 2 times 3 times 1, which equals 6. Add the 3. Nabla.a at p equals 4 plus 12 plus 6, which is 22. Interpretation. The divergence is positive at p. If A were the velocity of a fluid, more fluid would be leaving a tiny box around P than entering. P behaves like a source for this field. If we picked a different point, the answer would change. Divergence is a local quantity. Worked example 2. Spherical. And this is the example that every electromagnetic student should keep in their pocket. Take A equal to 1 over r squared in the r hat direction. This is the famous inverse square radial field. The electric field outside a point charge looks like this. The gravitational field outside a point mass looks like this. Anything spherically symmetric and falling off as 1 over r squared looks like this. Find the divergence. The spherical formula has 3 terms, but A only has an r hat component, so only the r term matters. Nabla.A equals 1 over r squared times the partial with respect to r of r squared times ar. Plug in ar equals 1 over r squared. The expression inside the derivative becomes r squared times 1 over r squared, which is just 1. The derivative of 1 with respect to r is 0. So nabla.a equals 1 over r squared times 0, which is 0, for every r greater than 0. Stop and feel that. Everywhere in space, except at the origin, this radial inverse square field has 0 divergence. If you draw a tiny box anywhere off the origin, the same number of field lines enter as leave. There are no sources out there. All the source is concentrated at the origin, where the formula breaks down. That is the mathematical heart of Gauss's law. A point charge produces a 1 over r squared field whose divergence is 0 everywhere except where the charge sits, and integrating around the charge always gives the same total outflow, no matter how big or small your surface. This is going to come back many times in this course. Quick recap. Divergence turns a vector field into a scalar. It measures net outflow per unit volume. Positive means a source, negative means a sink, 0 means solenoidal. The formulas. Cartesian, partial ax over x plus partial ay over y plus partial az over z. Cylindrical, 1 over rho times partial of rho a rho with respect to rho, plus 1 over rho times partial a phi with respect to phi, plus partial az with respect to z. Spherical, 1 over r squared times partial of r squared ar with respect to r, plus 1 over r sine theta times partial of sine theta a theta with respect to theta, plus 1 over r sine theta times partial a phi with respect to phi. The volume scale factors live inside the derivatives for the radial terms. That is the part students miss most. 2 answers. Cartesian, a equals x squared y plus y squared z plus z squared x at p1, 2, 3. Divergence equals 22. Spherical, a equals 1 over r squared times r hat. Divergence equals 0, anywhere away from the origin. Next worked example, the curl, the third differential operator. See you then.